Okay, if we have the real world situation here that we're really kind of looking at is where you have a driving force of the form, something, if you're driving force for for some oscillating system that's oscillating with drag, and you're driving it with a frequency, fancy omega. Okay, that's a fancy omega to distinguish it from the other omega that we often get when we do oscillating systems. Okay, if you get this driving force, how does the system respond? Well, we know that a system with a linear restoring force, which we assume, and a linear drag force, which we assume, is going to have this equation. Your my double prime is going to equal some multiple gamma of your y prime, that's your velocity, okay, that's your drag force, we've talked a lot about that, and your linear restoring force. So when you divide through by m and bring all this on the other side, you get this. And if it's just a plain old homogeneous equation, you just set it equal to 0. But if you're, and so you just get the thing started and then see how it behaves. If you're driving it with a periodic force, like a cosine, so you're giving it a force kind of like this, it's going to tend to oscillate. So the question is how? Well, in this case, let's just say we had this equation equal to cosine omega t. Just to review quickly, we solve the homogeneous equation, we get our R values, we get our fundamental set, and we get our solutions. And then we can assume a particular solution of the form cosine fancy omega t plus some multiple of cosine fancy omega t and sine of fancy omega t. Okay? And that's our variation, our undetermined coefficients. If we had this, well, this works because we know that the higher derivatives of this function always give us sines and cosines. So we're going to be able to get a cosine out of it. We've done that, so we should be familiar with that. If we have a tangent, it's hopeless to figure out what kind of functions you would take combine second derivatives, first derivatives with the function itself, and get a tangent out of it. Go ahead and think about it, but you're not going to get anywhere, neither will I. Okay? There are good reasons for that. So we're going to digress the general situation. What you do when you have this, you assume, first of all, you have an equation, and it doesn't have to have constant coefficients. Okay, you got an equation here with some non-homogeneous term, and we assume that we've been able to solve this equation. We have independent solutions y1 and y2. Based on those assumptions or functions, we assume a solution u1 of t, y1 of t, plus u2 of t, y2 of t. Well, we're going to have to plug this function in here and see if we can figure out what u1 and u2 are. So here's our function. We're going to have to plug it into the equations. We're going to know what the derivative and second derivative of this function are. The first derivative is very straightforward. Product rule gives us this. We can put two conditions on this thing, okay? Because it's a second order equation, and we'll talk a little bit more about that. But one condition we're going to put on it, we're going to have to take another derivative of this thing. We don't mind getting second derivatives of y1 and y2 because we already know what those functions are. What we want is, we don't want to see u1 double primes and u2 double primes if we can help it. So we're going to assume that these two terms add up to 0. So we assume this is 0, so now your yp prime is just this, and the second derivative only has 4 terms on it, rather than the 8 terms you'd have if you didn't make this, and you don't have any u1 double primes or u2 double primes. You've got y1 double prime and y2 double prime, but that's fine, we know what the functions are. Okay, so we're going to plug this into the equation, okay? And then what do we get? Well, we're going to see in the next clip.